for symmetry reduction. So let's start with a very short introduction about semi-definite programs. So we're minimizing a linear function subject to some linear constraints, ax equals b. What is special is that the matrix variable x is assumed to be positive semi-definite. And the feasible region of a semi-definite program is called a spectral hedron. The reason why it's called spectral hedron is that this matrix variable x is assumed to be positive semi-definite, meaning that the eigenvalues of x has to be non-negative, and therefore you see spectrum here. You see hedron because it's a generalization of polyhedron. So that's the reason why it's called spectrum hedron. So as a generalization of polyhedron, semi-definite program is much more expensive to solve than linear program, whose feasible region is a polyhedron. We are only able to solve small SDP instances. And that means a lot of interesting applications in practice are just not solvable by computer. And the second problem of semi-definite program is even worse. If you do not model the problem carefully, then you may not be able to find the solution correctly due to numerical issues. Say, if I have a model whose solution is the winner of the 2020 presidential election, but the model can never be solved correctly, then nobody is going to be interested in this model. So the ability to solve the model is also very important. Fortunately, we have two techniques to resolve those two problems, at least partially. Symmetry reduction tries to exploit the problem structure and reduce the size of the SDP. And while feature reduction ensures that the SDP instance can be solved correctly, or at least a reformulation of an SDP can be solved correctly. So I'm going to give a short introduction to symmetry reduction. 2 minutes crash course. We had the feasible region of an SDP, which is a spectral hedron here. What's important is this positive semi-definite constraint. In symmetry reduction, we try to address this positive semi-definite constraint by simplifying it into smaller PSD constraints. How do we do that? We try to find an orthogonal matrix Q such that for any feasible matrix X, the orthogonal transformation Q transpose XQ is a block diagonal matrix. So pick any feasible matrix X, compute this orthogonal transformation here, you always end up in the same block. You always end up with a block diagonal matrix of the same form, where Xi is the ith block of size Ni by Ni. And of course, the size have to sum to N. So that means instead of checking this matrix X of size N is positive semi-definite, I could as well equivalently check each small blocks is positive semi-definite. And checking a smaller matrix in positive semi-definite is a much easier task. So that means I can formulate my SDP, the feasible region of my SDP equivalently by replacing the PSD matrix X of size N positive semi-definite by Xi, the smaller blocks in positive semi-definite. This can be a huge reduction in the problem size. For example, if each small block is just a 1-by-1 matrix, then the semi-definite program collapses into a linear program. Because checking a 1-by-1 matrix is positive semi-definite is equivalent to say this number is non-negative. And this is not a crazy theory example. In practice, there are examples in practice that you can see that SDP is SDP relaxation collapse into a linear program. A concrete example, this is an SDP relaxation for the cut minimization problem, where X is a PSD variable. So I will skip the actual problem definition, which is not important here anyway. What matters most is this is an SDP relaxation for the cut minimization problem with the matrix variable of size n times k, where n is the number of vertices in a given graph and k is the number of subsets in partition. So if you pick a graph called CN161, you've got 161 vertices, and if we are looking for 3 partitions, then this results in an SDP relaxation whose size is nearly 500. And this is very difficult to solve. It crashes your machine right away, actually, because the memory demands by interior components. So hard to solve. This is the idea of this size. But the good thing is that the feasible solutions of this problem instance has certain symmetry, and therefore we can find a unitary transformation Q so that it brings every feasible matrix into this block diagonal form. That means instead of solve a problem with a PSD variable of size 500 by 500, we can instead working on a problem with smaller blocks whose size is at most 60. That is a very big difference. For most of the machines, you're not able to solve a problem whose size is 500 by 500, but you can easily solve one with 60 by 60 matrices in your laptop. So in the formulation, you will replace, as we mentioned already, this big PSD constraint by some smaller PSD constraint, and the size is reduced in this way, pretty obvious, and suddenly you can solve it in your laptop. It wasn't possible, trust me, it wasn't possible in any laptop, personal laptop. It probably eats more than 50 gigabyte memory. I don't think we have such a big laptop. Okay, so next question, how do we find this unitary matrix Q? Where do we get this? Can you always get this? The answer, since I only have 15 minutes, I got to skip this part. But the short answer is that
sorry, not 15, 50, 50.
Oh, 50. Oh, I'm sorry. I was rushing for it. Okay, I can slow down. Thank you. Thank you for letting me know. I see. Okay, then we have a lot of time left, and I can go slower. Okay, let's do it. So we had some okay, so let's go slowly. Symmetry reduction brings the big blocks, a big PSD matrix, into smaller PSD matrix by finding a unitary transformation Q. So the next important question is, where is this unitary transformation? Can you always find this unitary transformation? Is it difficult to find this unitary transformation? Let's answer this question now. It turns out that many problems have a natural symmetry, a combinatorial symmetry, or just a symmetry, whatever it is. Here, let's say we have a combinatorial symmetry. For example, if your problem is defined on a graph, your input graph might be invariant under certain permutations of its vertices. For example, if you take a full cycle here, a cycle with 4 vertices, if you rotate it clockwise, you get the same graph. It's still a 4 cycle. If you flip horizontally, you still get a 4 cycle. So this graph is invariant under these 2 permutations of its vertices. And actually, these 2 permutations form a group that's called and all the members in this group is a permutation that keeps the same graph. So it turns out that the symmetries in the problem, for example, the permutations of this input graph can be translated into symmetries of the data matrices of our SDP relaxation. So that's pretty natural because you construct your SDP relaxation based on your input graph. And so what do we mean symmetries in the data matrices? Let's introduce one terminology here. A set of matrices is a matrix star algebra if it satisfies certain rules. For example, it's closed under addition. Then, namely, that means if you pick two matrices from this set, then their summation is again contained in this set. And similarly, scalar and matrix multiplication and taking conjugate transpose, all those operations are closed in this set. So a matrix star algebra is nothing special, but a subset of matrices satisfying certain properties, certain closeness properties. So what is special about the data matrices C in the objective and data matrix A1 to AM is that if your original problem has certain symmetries in this way, this combinatorial symmetry, then this translates into a symmetry in data matrices in the sense that the data matrices are contained in some matrix star algebra. Yeah, that's a symmetry we mean here. And what does this mean? It has two important consequences. If an SDP whose data matrices are contained in a matrix star algebra. Two consequences. The first consequence, if my data matrices and identity matrix are contained in a matrix star algebra, this result from the Clerk 2009 shows that then we claim that in SDP, there exists an optimal solution in the matrix star algebra M, if this SDP has an optimal solution. That's a very nice property. It is not very difficult to show this, but it has a very nice consequence. So instead of trying to optimize over the original set of original feasible region, since we know that there exists an optimal solution in this matrix star algebra, so I can as well try to optimize the feasible region intersect this matrix star algebra, since I know that there exists an optimal solution there. So that makes my feasible region smaller. And not only that, because I know that my feasible region is now contained in a matrix star algebra, the second theorem from Wonderberg shows that there always exists a unitary matrix Q, so that the matrices, any matrix Q, any matrix in the matrix star algebra M containing identity matrix can be decomposed into block diagonal matrices, into a block diagonal matrix in this form. So these two theorems together means that if I have an SDP, if I have a problem and there is a symmetry in the problem, then I can translate this symmetry in the problem into symmetries in the data matrices in the sense that the data matrices are contained in some matrix star algebra. Then this first theorem says I can restrict the feasible region to the matrices in this star algebra. So I can replace my problem, replace the feasible region of my problem equivalently by a subset of a subset defined by the intersection of the intersects the matrix star algebra M here. So all my feasible matrices are contained in some matrix star algebra. And then I can use my second theorem to show that there exists a unitary matrix Q, which is going to decompose all my feasible matrices into a block matrix. So this is just one way to find this unitary transformation Q. There are also more general approach to find this decomposition here, but they are all the same flavor. So are there any questions for this part, symmetry reduction?
You have a question in the chat from Faye.
Yeah.
Can you show an example of a graph that is not invariant under permutations?
Yeah, this is my question.
Yeah. Sorry. Could you say your question again? Sorry, I didn't hear clearly. Could you?
Oh, yeah, it's a question from Faye. It's in the chat. Can you show?
Oh, it's in the chat. Yeah. How can I? Let me see. Oh, I see the chat. Yeah. Can you show an example that a graph is not invariant under permutation? Yes, there are examples that a graph is not invariant under any permutation. Let me see. So I think in general, if you just say fix for a fixed number of vertices, if you just randomly generate some edges, then remove all those isolated vertices, then what you get will be a graph that is that cannot be permitted in any ways to get the same graph. And yeah.
As if you take any graph where the vertices have different degrees, right?
Yeah. If the vertices are different of different degrees, then you can permit. Yeah, you are right. So one of the so if the graph is invariant under certain permutation, so if one vertex can be mapped to another vertex, so a necessary condition is that they have the same degree. I don't think this is always possible, and I've seen a lot of examples that it is not possible. But for now, I can't come up with a minimal example. What is a minimal example here? But I'm pretty sure there are a lot of examples, but I don't have a small example to present here. Does that answer your question?
Yeah.
Okay, thank you. All right. Let's move to our second topic, feature reduction. So, status condition, or sometimes called strict feasibility, is a constraint qualification for convex optimization problems. And in case of semi-definite program in standard form, it requires the existence of a feasible matrix X. Well, of course, it's feasible, satisfies all the equations, all the equality constraints, and moreover, it has to be in the interior of the PSD cone. So it has to be positive definite instead of positive semi-definite. So this constraint qualification is important because if you don't have strict feasibility, many bad things can happen. For example, the conductor conditions may not be necessary for the optimality. And strong duality may not hold. Many algorithms are solving the prime and dual problem at the same time. Sometimes you're trying to find the optimal solution of the dual, but there is a duality gap. Problems like this can happen. small perturbations may render the problem infeasible. So if you change your problem slightly, then the problem becomes infeasible. So in case there's noise, it can be a huge issue. Many solvers might run into numerical issues. So those solvers are very successful in the practice. Most of the problems can be solved. But here, if you have a structural problem without Slater's condition, those solvers can still fail miserably. So this is also one of the reasons semi-definite program is less popular than its special case linear program, because people just throw it into the solver and they can't solve it correctly. That makes it less interesting. So as an optimizer, those things, that means we have a lot of things to improve. Feature reduction is a regularization technique which brings semi-definite program into an equivalent form, so that it can it will satisfy the status condition. So this is one of the methods that can restore Slater's condition if a given SDP does not satisfy Slater's condition. And the loss of strict feasibility is a common issue in SDP relaxations for hard non-convex problems. So in general, if you randomly generate an SDP instance, it turns out that the Slater's condition always holds, like with probability almost 1. But in general, for problems in practice, usually it has certain type of structure coming from the problem structure, and very often Slater's condition doesn't hold for those problems. So let's look at feature reduction algorithm. What it does, it is essentially the separating hyperplane theorem. So let's consider the semi-definite program in standard form, given as follows. Then exactly one of the following alternatives hold. First, the semi-definite program 1 here is strictly feasible. So there exists a matrix AX equals B and X is positive definite. And in this case, we're happy and the story ends. If it is not strictly feasible, then the auxiliary system is consistent. Namely, we can find a vector Y so that A star Y is a non-zero positive semi-definite matrix and BY equals 0. So this is the engine of feature reduction, and this theorem is actually nothing special except the hyperplane separation theorem. Why? If SDP is strict feasible, then there is matrix X satisfying both constraints. Now, if you treat it separately, the matrix satisfies the set of matrices determined by this equation. This is just a linear subspace. It's a convex set, right? And the set of matrices in the interior of the PSD cone, or the set of positive definite matrices, is also a convex cone. So that means if SDP1 is not strictly feasible, that means these two convex sets, the convex set determined by this linear equation, and the convex set, which is just the set of positive definite matrices, those two convex sets do not intersect. If one failed, that means those two convex sets do not intersect. But then the hyperplane separation theorem says that there exists a hyperplane separating those two convex sets. And this hyperplane is actually this A star Y here. So this is actually equivalent to the hyperplane separation theorem. But in the context of Fisher reduction, we call this hyperplane, this separating hyperplane, a star y, an exposing vector. Okay, that's only the first part of the story. Now the second part comes with this observation. If the SDP1 is not strictly feasible, we find an exposing vector. But then the feasible region of this, our SDP, is contained in the orthogonal complement of this exposing vector intersect this PSD. So for those who are familiar with convex analysis, this is a phase of the PSD cone. And that means I can restrict myself into a smaller phase of the PSD cone, which is the smaller PSD matrix. And therefore, we have reduced the problem size. And that means the Fisher reduction algorithm can proceed as follows. Given an SDP relaxation, we try to find an exposing vector A star y. We try to solve this system, find an exposing vector A star y. If we could not find this, it means the first item is correct. We are strictly feasible. If we could find one, then we have reduced the problem size to obtain a new formulation. And we can repeat. Since the problem size is finite, we're going to eventually stop. The algorithm is eventually going to stop at a certain stage. And at that time, we must have a strictly feasible formulation. So this is how Fisher reduction works. In the cut minimization problem, we have this SDP formulation. And if we perform Fisher reduction, then we're going to replace the positive semi-definite constraint on X by this linear equality constraint, X equals VRV transpose, where R is our new PSD constraint. You can see that it becomes a smaller PSD constraint now, which is only of size n-1 times p-1. And actually, it's become strictly feasible. There exists a feasible solution R, which is positive definite of this size. In terms of size, we see that the original problem is nearly 500, and after the Fisher reduction, the size becomes only around 300. So in terms of size reduction, we see that symmetry reduction did a lot better, but I would like to note that this is not the main goal of Fisher reduction. The main idea of Fisher reduction is that we would like to have a stable formulation which can be solved correctly, and as a byproduct, the PSD problem size is also reduced. So an natural idea is that can we do both Fisher reduction and symmetry reduction so that we can enjoy both properties? Namely, we can have a smaller problem and we can also solve it in a stable manner. So that's the idea of our work. We would like to combine Fisher reduction and symmetry reduction. So what is the main problem here? So we have introduced the techniques Fisher reduction and symmetry reduction. Actually, in theory, there is no problem to apply both Fisher reduction and symmetry reduction. Those two theories are just independent theories, and in theory, it works for any SDP relaxation. So you can always pick any SDP relaxation, apply Fisher reduction, at the end you still have an SDP relaxation, then you apply symmetry reduction. Or you can do in another order. There's no problem. But in practice, it is not possible. Because, for example, if you apply Fisher reduction first, and then you would like to apply symmetry reduction. But where is the symmetry now? For example, you start with a problem defined on a graph, but after feature reduction, it becomes something that you do not recognize its structure anymore. We have examples that you might lose all the symmetries after feature reduction. So that makes it very difficult to apply those two techniques together. And so what people do currently, they either do feature reduction only, and that means they are only able to solve small instances. Or we do symmetry reductions only. But that means the solution we find may be very inaccurate. And this is sometimes a topic that is a bit underestimated in the community. They take whatever the solver reports at the end, but the solution can be really, really far away from the true optimal solution. And what is worse, if you're looking for a lower bound for some hard problem, if you are not solving it correctly, sometimes it may not give you a lower bound. That means you are doing nothing if the result you get is not a lower bound even. So our contribution here is that we come up with a method which finds a formulation that is both visually and symmetry reduced, so that if you solve it, you are not only able to solve it, but you are able to solve it accurately. So here is our main result. Recall that exposing vector is the term I mentioned when we look at the feature reduction algorithm. So if W is an exposing vector of the minimal phase of a given SDP instance, so the minimality here means that if you use this exposing vector to get a smaller SDP instance, then the reformulated SDP instance is going to be strictly feasible. That's what the minimality here means. So if we know an exposing vector for the original SDP instance, we show the following two things. First, there exists an exposing vector in the algebra of the minimal phase of the input SDP instance. So we are not only having an exposing vector, but an exposing vector in a special form. And second, this is the most important one. Q transpose WGQ is going to be an exposing vector of the minimal phase of the symmetry reduced SDP. So that means if I use this exposing vector here, I will find a strictly feasible formulation for the symmetry reduced SDP. And therefore, we have found a formulation that is both visually and symmetry reduced. So here maybe it looks complicated, but in plain words, it's just nothing else, but we know how to do feature reduction for symmetry reduced SDP. So what does it mean in our cut minimization example? Here is just an SDP relaxation for the cut minimization example that you've seen before. And here's the symmetry reduced program where we have replaced our PSD constraint by some smaller PSD constraint, where Ni is typically much smaller than where it should be Nk here, where the size sums up to Nk. And what we did is that we find a visually reduced formulation for the symmetry reduced program. And it ends up with a formulation that is both visually and symmetry reduced. And that means for each block here, xi, it is in the PSD cone of size ni. We're going to replace this by an equality constraint xi equals BRV transpose, which is the face of this PSD cone, and Ri is in a probably an even smaller PSD cone, Ri. So each matrix variable Ri is going to be a smaller cone than Ni, and sum of them is going to be strictly smaller than Ni. So for the CN161 instance, in our cut minimization example, we'll observe the following thing. If you perform both visually and symmetry reduced program, you still end up with all those smaller blocks. And each block becomes even smaller than the one you had from symmetry reduced program. So let me repeat. We are given an SDP relaxation whose size might be too big to solve it. And in this case, we have a PSC constraint of size 483, and this is just too big to solve for, I think, for any SDP solver, interior point SDP solver. You can do feature reduction. That means you can solve these problems accurately, but the size are still too big here. You could do symmetry reduction. Then you end up with some smaller blocks, which you can solve it by the interior point method, but the answer you get might be inaccurate. And here's our contribution. We combine these two techniques. We end up with a problem with size smaller, and also it can be solved accurately. So that's a lot of promise, but those are all theories. When I say the problem cannot be solved, it is easy to verify because if you throw it in your computer, it will indeed crash your machine. Then you will not do it again next time. But how about this statement that you cannot solve it accurately, but then you can solve it accurately? But maybe this is not the case. It's just your theory. You're just trying to sell us your products, your paper, so you are exaggerating the situation. I'm going to provide some numerical examples for those instances. Here, we solved the SDP relaxation for the cut minimization problem using interior point method. So let's see what we get. So this is instance we have solved. We have bound iteration time and what the solver said to us at the end when it finishes. Here in the third column, we are solving the symmetry reduced problem. And in the fourth column, we are solving the visually and symmetry reduced program. So note that for both original program and visually reduced program, we cannot solve it at all because the size is too big, it crashes your machine. And when you solve the symmetry reduced program, which people did currently, then the solver will say at the end, he fails and he cannot find an accurate solution. And it takes a lot of time and it takes a lot of iterations. And actually for interior point method, if you observe that it takes anything like more than 30, it's a strong signal to you that something went wrong because it converged in theory quadratically to the optimal solution. So if it ever takes more than 30 iterations, it's a signal something went wrong. And it finds you a bound. And he says he doesn't know if he has solved correctly. So let's try to solve the visually and symmetry reduced program, which in theory means that we can solve it correctly. And you run this, and the solver indeed tells you that, oh, we found the optimal solution. Everything was successful. There's no problem. We observe that it takes much less time. And also the number of iterations is 18, which is a reasonable number for interior point method. And moreover, you see that the bound is significantly different from the one you obtained from by solving the symmetry reduced program. Because by solving the symmetry reduced program, because of the ear conditioning, because it doesn't satisfy the status condition, the solver couldn't find the optimal solution, but instead, in this case, he just finds something which is as close as possible as he could. But you see that if you get something that is so far from the actual optimal solution, then you lose all the purpose of doing semi-definite program, which is more expensive, but provides you a very strong lower bound or upper bound. But here you see that it probably is weaker than some trivial lower bound in this case. So without solving the model correctly, it doesn't make sense. And similarly, this CAN 161 is the example I presented. If you try to solve the symmetry reduced program and visually and symmetry reduced program, you observe exactly the same thing. We can solve it in a shorter amount of time. We get a better lower bound. We're supposed to get the same bound, but we are getting correct lower bound here. And we're using less iteration. So this is pretty much what we observe in practice. So that means it's really important to do feature reduction and symmetry reduction together. And at least if you want to solve it correctly, feature reduction is something that you cannot miss. So there's one more contribution from our work. It turns out that our framework fits very well in a first order method called ADMM, because when I said interior point method in the last 15 minutes, people may come up with the question that, okay, interior point method as a second order method, it's just too expensive. How can you switch to a first order method? And this is indeed possible in this case. Because after symmetry reduction and feature reduction, we have very natural splitting of the variables. Recall that we replace the PSD variable, PSD constraint x in x positive semi-definite by the equation x equals V transpose, where x and r are both variables. So this is a very natural splitting, and it is this natural splitting end up with a very good implementation in ADMM approach. So ADMM split your problem into two smaller subproblems. And because of how our formulation looks like after symmetry and feature reduction, the subproblems in ADMM is extremely simple. So at each iteration, you get your subproblems. One of your subproblem is solved explicitly. You get an explicit formula. And another subproblem is equivalent to a spectral decomposition. So both subproblems can be solved extremely simple. And that's the key in a first order method like ADMM. And this enables us to solve some huge SDP instances. For example, for the quadratic assignment problem, we are able to solve problems whose size is even 500 by 500. This is just a huge instance. For example, interior point methods cannot even handle problems with any 30 here, but we are able to solve 500. And even you look at the other first order method, the best thing they can do is around the size 64 and takes quite a while. It's even longer than the time we spent here for this size 500. So we are solving huge instances by using this technique. But of course, it doesn't always happen. We have to assume that there are certain symmetries in the problem. Otherwise, symmetry reduction is doing nothing. You can't run a car without the fuel. It needs the fuel, which is symmetry here. So as a comparison, for example, the best result for those instances, for Harper instances, are coming from this paper by Miltman and Pong. You see that it takes them quite a while to solve this instance of 128. Takes us we are 10 times faster than their running time, and we can go even higher. A little price we have to pay here is that the second order method, like interior point method, is slower for big instances. Sometimes it's just most likely it's impossible to solve it. But whenever it is possible, it arrives at a very accurate solution, assuming Slater's condition, of course. For the first order method, you will get something near the optimal solution very, very quickly in a few hundred or thousand iterations. But then it's very difficult to get a very accurate solution, even it is possible in theory. So a little price we pay here is that this bound is not so accurately solved. But we do guarantee that this is a lower bound. That's very important. Yeah. Well, I guess I'm running out of time, but I'm also finished now. So thank you for presenting in this session. Thank Daniel for inviting me to this talk. Thank you.